Okay, everyone, for the video lecture for Chapter 22, we're going to discuss a slightly different version of the chi-square test that we talked about in Chapter 21. Chi-square test in Chapter 21 was basically what's called a one-way chi-square, essentially very, very straightforward. In Chapter 22, we're going to do what's called a two-way or a two-factor chi-square, or more specifically a chi-square test for two-way tables. This is where we're going to look at two separate categorical variables and the different levels of each to see if we can find any relationships between them. Now again, in this one we're going to be looking at expected proportions for some variable versus actual or measured proportions to see if the two differ significantly from one another. All right, so let's move on with this here. So whenever we're talking about a two-way test or a two-way table, let's say that, it's also called a block design. Sometimes you refer to it as, or see it referred to as a two-way or a block design. And basically what this means is that we're going to have two separate categorical factors or variables, and each one is going to exist in several levels. Okay, so several levels of each factor. All right. So as an example, let's say we want to know if there's a relationship between the smoking status of a student's parents and that student's smoking status. In other words, would you expect or do you see any evidence that students who are raised in two-parent smoking households are more likely themselves to smoke or not? That's the main idea here. So here in the bottom of this slide, high school students were asked whether they smoke and whether their parents smoke. So we have two different sort of variables here. One of them is student smoking status, and you see that here on the table. The other variable is parent smoking status, and you see that on the side. So for student smoking status, we have two levels. Either the student smokes or the student does not smoke. For parent smoking status, we have three. Both parents smoking, only one smoking, or neither parent smoking. So, three levels of parent smoking status, two levels of student smoking status, and here we actually see the data for that. So, the data here, when you're looking at it this way in a table, it's hard to sort of glean any information about whether or not there's a relationship here. And this is what the chi-square for two-way tables is going to help us to figure out, okay? All right, so just as an example, here we have 400 students who said they smoked and also lived in a two-parent smoking household. Here we had 1,380 students who identified as not smoking, but also lived in a two-parent smoking household, okay? So the relationships can be quite complicated, but the two-way or chi-square for two-way tables makes it pretty simple to figure out if there's a significant relationship between either of these two variables. Okay, so what we have to look at here, first of all, and this is really the first thing that differs between this and the chi-square we talked about in Chapter 21, is what are called the marginal distributions. Okay, so these are the distributions in the margins of the table. They're going to summarize each factor separately or independently. So we have a marginal distribution here, for example, in this column, marginal distribution here in the row or the column totals. So both parents smoking, 400 plus 1,380 gives us a total of 1,780 students who said that both their parents smoked. 2239 said only one parent smokes, and 1356 said neither parent smoked. Now, of all these students, so there's 5,375 students, of all of those, 1,004 said they smoked, and 4,371 said they did not. So what we're looking at here are the marginal distributions. So what is the probability then, in this case, given the data in this table, that a student lives in a two-parent smoking household? All right. Well, we take 1,780, which is the total number of students who live in a two-parent smoking household, and divide that by the total number of students. So 1,780 over 5,375, 33.1% of our students live in a two-parent smoking household. Probability that one parent smokes, 41.7%. So 2239 over 5,375 gives you 41.7%. The probability that neither parent smokes, 25.2%. So 1356 over 5375 is 25.2%. So these marginal distributions are helpful for converting our actual data into proportional data, okay? And here we see a summary bar graph of these proportions that we just figured out. All right, now we also have marginal distributions for the student smoking data. So what is the probability that a student smokes? Well, 1,004 of our 5375 students said they smoked, so 1,004 divided by 5375, 18.7%. And the probability that a student doesn't smoke is 4371 divided by 5375, 81.3%. So here we see the summary bar chart for that, for those distributions, those marginal distributions, okay? All right, so once we have the marginal distributions, then we can start looking at what are called the conditional distributions. The conditional distributions represent the data in the interior of our two-way table. So the cells of our two-way table then represent the intersection of a given level of one variable, say student smoking status, with a given level of the other variable, parent smoking status. So, for example, students who smoke, 400, but also lived in a two-parent smoking household, right there. 400 is the number of students that identified as smoking, yet also lived in a two-parent smoking household. This number is conditional on these two levels of these two variables. Likewise, this number is conditional on this student smoking status, this level of student smoking status, and this level of parent smoking status. That's why we call these conditional distributions. They're dependent on the various levels of the two variables that we're looking at, okay? All right, so what's the probability then that a student smokes and lives in a two-parent smoking household? 400 divided by 1780, 22.5%. What's the probability that a student smokes and lives in a one-parent household? 416 divided by 2239, 18.6%, and so on down the line. All right, and so here you can see an interesting bar chart. So we see that the highest number, if this is percent of students who smoke, the highest percentage of students who smoke is found in two-parent smoking households. Intermediate proportion of students smoking is found in one-parent smoking households, and the fewest number of students smoking is found in neither parent smoking households. So that seems to agree with what you would expect going into this. But as always in statistics, we have to look at these differences here statistically to see if we find significant differences, okay? To determine if that's random variation or if that's a real effect of parent smoking status on student smoking behavior. All right, so let's talk about hypotheses. So a two-way table has a certain number of rows and a certain number of columns. It's referred to as R number of rows and C number of columns. The null hypothesis here is really simple. It's really straightforward. It simply says that there is no relationship between the row and column variables. That's it. It's very, very general. It's much more general than the null hypotheses we've seen previously. Again, our null hypothesis here just says that there's no relationship between our row and column variables, whatever they might be. The alternative is just as simple. It says there is an association or a relationship between the two variables that we're looking at. So what we're going to do here is compare our actual data, our actual counts, with those we expect under the null hypothesis. So again, we're comparing actual to expected, or observed, which is actual, observed being compared to expected, to then determine if we should accept or reject our null hypothesis. Okay, so a two-way table has, again, a certain number of rows and a certain number of columns, and we know that our null says there's no relationship between those two variables. So how do we calculate our expected counts? Okay, well, let me fill in the table here a little bit. Okay, so the expected counts here are really simple. We simply take our row total and multiply that by our column total and divide it by our table total. So we have to do this for each of our conditional distributions in the center of the table, okay? So again, our row total times our column total divided by our table total. And we're going to see here in a couple of slides how it is we go about doing that. But let's set up a situation or a scenario for looking at this. All right, cocaine addiction. Cocaine produces short-term feelings of physical and mental well-being. To maintain the effect, the drug may have to be taken more frequently and at higher doses. After stopping use, users will feel tired, sleepy, and depressed. A study compares the rates of successful rehab for cocaine addicts following one of three treatment options. There's antidepressant, disipramine. It's a fairly new treatment. There's a standard treatment, which is lithium, and there's a placebo, which is sugar pill. So this study is looking to see if any one of these three treatments effectively reduces depression and therefore helps to prevent relapse. Relapse is when somebody goes off of a drug, but then because of the effects of going off the drug, they go back to the drug because the symptoms of going off the drug are so severe. So relapse is a bad thing. All right, so you see in our table down here that we had for disipramine, we had a total of 25 people taking that drug. 15 of them did not relapse, which is good. 10 did. For lithium, we had a total of 26 people. 7 did not relapse, and 19 that did. That's a pretty high relapse rate. For placebo, of the 23 that took it, that had placebo, we had 4 that did not relapse, 19 that did. All right. So we had a total then of 26 across our entire study who did not relapse and 48 that did. All right, so let's take a look at our table here. Okay, so here we see our data. So that's our two-way table. You see we have our column totals here, which we just looked at, and we have our table totals. So 25 on disipramine, 26 on lithium, and 23 on placebo, 26 who did not relapse, 48 who did, total of 74 study subjects. So remember, we have to calculate our expected counts. And expected counts, again, go back a couple of slides, are the row total multiplied by the column total divided by the table total. So here we have we have an expected count of 8.78 for disipramine and no relapse. Well, how did we come to that? So row total, 25, right there, times our table total, times our column total of 26 here, divided by our table total of 74, gives us 8.78. Over here, we have row total of 25 times column total of 48, so 25 times 48 divided by 74 gives us 16.22. So you see we have expected counts of 8.78 for disipramine and no relapse, 16.22 for disipramine and relapse. We have 9.14 for lithium and no relapse, 16.86 for lithium and relapse. We have 8.08 expected for placebo and no relapse, and 14.92 for placebo and relapse. These are our expected counts. All right, now, expected percents. What we look for in terms of our expected percents is basically that they're all the same, and you can see that right here. Okay, under a null hypothesis, we wouldn't expect any one of these three treatments to be any more or less effective than the others. Okay, so basically, what we're looking at here is a situation where none of the drugs is effective, really, or if any of them are effective, they're all effective at the same level. That's our null hypothesis. And we're looking to see if our expected counts meet up with those expectations, okay? Or I'm sorry, our observed counts meet up with those expectations. And that's the whole point of the chi-square analysis. So, chi-square test for two-way tables looks for evidence of an association between two categorical variables. In this case, what drug's being used and whether or not there was relapse on that drug. Okay, so we can draw these samples in a couple of different ways by randomly selecting random samples from different populations or from populations subjected to different treatments. So just as an example, maybe you have girls vaccinated for HPV or not among 8th graders and 12th graders. So Here you'd have vaccination status, vaccinated or not, and you'd have two different levels of grade, 8th and 12th. Remission or no remission for different treatments, okay? You could do it by taking one random sample and then sort of subdividing the sample, the individuals in the sample according to different categorical variables. So take a sample of all high school students, let's say, and then divide them by maybe obesity and ethnicity, all right? So there's a number of different ways that you can do this. Now, as with any of our inference tests and statistics that we've talked about, there are certain conditions that our data has to meet in order to be able to run a chi-square test on them. First of all, and these are actually the same conditions we saw in chapter 21 for the first kind of chi-square we talked about. First of all, very few or no more than 1 in 5 of our expected counts can be less than 5. Secondly, all expected counts must be greater than or equal to 1. All right, so as long as our data meet those two requirements, then we can do a chi-square. It's pretty simple. Now, let's say that we have a situation where we've got our data and one factor or the other has expected counts that don't meet these criteria, okay? You could, if you have too many different levels, you could collapse some of your levels, okay? Maybe you have 5 different levels, you could collapse it to 3 depending on what the levels of that variable are. Maybe collapse 5 down to 3, and that gets you around this problem by increasing your expected counts, okay? But it just depends on the situation. All right, so again, our null hypothesis here is that there's no relationship between the row and column variables, and the alternative is simply that that's not true. The alternative is that there's a relationship. So our chi-square statistic then, okay, equals the sum of our observed counts minus our expected counts squared divided by our expected counts. So this is the same formula we saw in chapter 21. All right, when our null hypothesis is true, the chi-square statistic follows the chi-square distribution with our rows minus 1 times column minus 1 degrees of freedom. So the way you calculate your degrees of freedom is take the number of rows and subtract 1 from it, and multiply that by the number of columns minus 1, okay? So this is how you calculate degrees of freedom, and again, that's going to tell you what row of the chi-square table to look at to find your chi-square statistic and then locate the p-value range based on that, all right? So let's take a look at our table. So let's say we have a situation where we have a degrees of freedom of 6. Means we're going to look on that row right there. Let's say we have a chi-square value of 15.9. So degrees of freedom of 6, find 15.9. Well, it's between these two numbers, go up. And we know our p-value is between 0.01 and 0.02. All right. Now again, remember that chi-square is values are only positive. You're only dealing with the right-hand side of the curve, the right-hand tail of the curve. So there's no two-sided option for p-value here. The p-values are one-sided options. Okay. All right, that's why there's not a second row there for p-value like you would see in a t-table or z-score table. All right, so let's go back and look at our drug use example with dicipramine, lithium, and all that, okay? So, oh, hold on, I gotta fill in some stuff here. iPad again, all right. Working on it, bear with me. Okay. All right, so first of all, degrees of freedom. So look at our table. We have 3 rows and 2 columns. So remember, our degrees of freedom here is rows minus 1 times columns minus 1. So rows, 3 minus 1 gives us 2 here, times columns 2 minus 1, 1, so 2 times 1, 2. Our degrees of freedom is 2. Now we know what row of our table to look at. All right, remember our chi-square calculation is observed minus expected squared over expected. So this first calculation here is for our upper left-hand cell in our table, right? 15 minus 8.78 squared divided by 8.78. The second part of the calculation is for decipermine relapse. So 10 minus 16.2 squared over 16.2, or divided by 16.2. We do the same thing for all of the rest of them. There are 6 calculations, 1 for each cell in our table. We add up all those individual contributions. We get a chi-square of 10.74. So, using table D, on degrees of freedom, row of 2, we find 10.74, and we see it lies between a p-value of 0.0025 and 0.005. So that's a pretty small p-value. Minitab would calculate it more precisely as 0.0047, and an alpha 0.05, we reject our null, which means there is evidence for a relationship between treatment type, decipermine, lithium, placebo, and the outcome. So these observed counts that we see up here, say 15, 10, 7, 19, 4, and 19, for example, are evidence of a relationship between what treatment person is on and whether or not they relapsed. All right, so we can reject our null hypothesis then of no relationship. But looking at the data here, it's kind of hard to tease apart and think about or figure out what that relationship might actually be. All that the chi-square value tells us is what our p-value is. And all the p-value does is tell us, well, that somewhere in here there's a relationship. It doesn't tell us what it is. So we need to dig a little further into this once we've rejected, or if we've rejected our null hypothesis, to try and figure out exactly what that relationship is. And so now let's talk about interpreting our chi-square output. And this is something that you need to do in your Minitab outputs when you do chi-squares in Minitab. So when our chi-square test is statistically significant, in other words, when we have rejected our null hypothesis, we want to look at the components. The components of this chi-square are each of those, in our drug example, each of those 6 calculations that we add up to get our chi-square value. The largest of those components will usually indicate what conditions are most different from what we expect, are most different from our null hypothesis. Okay, we can also look at those on a graph. But if we look at our components here, right, what we see is that decipermine and no relapse gave us the largest chi-square component. All right, we had the smallest components for lithium and next smallest for placebo. Placebo actually seemed to have more of a relationship than lithium did for some reason, but the important point here is decipermine. Okay, we have the largest components, first and second largest components, no relapse and relapse, respectively, for decipermine. If you look at the figure down here, percent of successes, right, what you see is that right there, 4.41, no relapse, that's a success, correlates with this high percentage of successes for decipermine. And that large component there of 4.41 is what's driving this significance here. That's why our p-value is significant, and also to a secondary extent, this large component for relapse as well. Okay, so it looks like decipermine is actually having an effect, more so than we would expect under our null hypothesis, more so than we would expect if there was no relationship here. All right, let's go back to the parental smoking example we talked about before. If you take that data and you put it into Minitab and tell Minitab to run a chi-square test for two-way tables on it, this is the output table that Minitab will give you. Okay, so again, we have random sample of high school students here. Our rows are parental smoking habits. The columns are the student smoking habits. Question is, what does it tell us? There's a lot of stuff going on here. This is kind of busy. But first of all, sample size. This number in the bottom right-hand corner, that's our sample size, okay? All right, what we see here are calculations for our contributions for each of the 6 different comparisons. So again, we have student smokes, both parents smoking. That's the chi-square calculation for that. Student smoke, one parent smoking. That's the calculation for that, all right? So look at the bottom. Here we have our chi-square summary. So 13.709, that is for the calculation of for student smoking and having both parents that smokes, right? Look at the next one, or the largest one actually, 16.829. That is for student smokes, but neither parent smokes, all right? Now, what you're seeing here is the observed value on top and the expected value on the bottom. So if you compare all these, you see that here we have a fairly large difference, 68, something like that. Here we have about the same in terms of difference, right? A large difference there. Look for student smokes and one parent smokes. There's almost no difference between what we see and what we expect. For students not smoking and both parents smoking, not as much difference between what we see and what we expect. Same is true here for no smoking for students and one parent smoking, right? So you're comparing the observed minus the expected to see what the difference is. And where you have the largest difference, that's where you get the largest contribution values. If you look, our overall chi-square is 37.6, and most of that comes from this comparison and this comparison. Those are the most different then from what we expect, right? Okay, so we see our sample size is 5375. What are our hypotheses? The hypotheses are that there's no association between parental smoking habits and student smoking habits, and that's our null. The alternative is that that's not true. Are the data okay for a chi-square test? Well, they are a random sample, and our expected counts are all greater than 5. You see that here, right? There's an expected count, expected, same thing. All greater than 5, so we're good there. So, what is our interpretation here? Well, look at our p-value, 0, effectively. So, there's good evidence, strong evidence of an association between parental and student smoking habits. Our p-value is less than 0.001 in this case, and especially it seems that students with no parent smoking are less likely to smoke, whereas students with both parents smoking are more likely to smoke than we would expect if there was no relationship. And that's essentially what these comparisons here are showing us, okay? All right, let's look at another example. So, 2013 Gallup study investigated how phrasing affects the opinions of Americans regarding physician-assisted suicide. Telephone interviews were conducted with a random sample of 1,535 adults. Using random assignment, 719 heard the question in Form A, end the patient's life by some painless means, and 816 heard it in Form B, assist the patient to commit suicide. And that's the key phrase, commit suicide right there. It has a very negative connotation to it. All right. So here's our data table, our two-way table. So we have painless means, 503 said allow it, commit suicide, 416 said allow it. Painless means, not allowed 194, 367 for commit suicide. And right there is probably our key difference, as you can see, okay? The chi-square test for these data turns out to be 57.88. That's a large chi-square. And so right now, if you know anything about the table at all, that tells you it's significant, okay? So we'll see that in a second. We're going to conclude here at an alpha of 0.05, and I can already tell you this is going to be significant. So the question is, which of these three options are we going to go with in terms of our results? There is significant evidence of a relationship between opinions and question wording. B, we failed to find significant evidence of a relationship between opinions and question wording. Or C, the test assumptions are not met. Well, again, with a large chi-square like that, A is the correct one here. Okay, the p-value is going to be really, really small and highly significant, very highly significant, actually. So we're going to reject our null hypothesis of no relationship with the way the question is phrased and the opinions expressed. This is a randomized experiment, and the expected counts are all greater than 5. You don't see them here, but they are. And so the test assumptions are met, okay? So let's take a look. All right, so we had a 3x2 table, so our degrees of freedom, again, as we saw earlier, is 2. So we're looking on row 2. You go all the way to the right, and the table sort of ends at 15.2. We have a chi-square of 57.88. So we know that our value is way off to the right of that. So it's very highly significant, less than 0.0005, as you see right here. And this tells us that the way that the question is phrased does have an impact on the way that people respond in these sorts of surveys, okay? The phrasing of painless means resulted in a substantially higher approval, 70%, than the phrasing of commit suicide, 51% in favor. And you can see that right here. So look at the orange section, not allowed. Painless means, far fewer said it was not allowed there, that way, than under commit suicide. For allowed, more people said it was allowed when the question was asked using the phrase painless means than when it was phrased using the phrase commit suicide. So we do find significant evidence here that the way that the question was phrased does actually affect the way that people respond. All right, so that's a chi-square test for two-way tables. Again, pretty basic. The major difference here is that the table is a little more complicated than in a one-factor chi-square that we saw in chapter 21. We have to calculate our marginal distributions, okay, our row totals and column totals, and we have a different way of calculating degrees of freedom, rows minus 1 times columns minus 1. But the actual chi-square calculation itself is exactly the same. The sum of the observed minus the expected squared divided by the expected for each of our conditional distributions in the body of the table. Okay? All right, that's it for chapter 22.